There is a point where distance stops feeling like distance and starts feeling like nonsense. You can picture the walk to your kitchen, the drive across town, even the road trip to another city. But try to imagine crossing the space between worlds, and your brain starts to slide. The numbers keep getting bigger, while your intuition stays stuck at the scale of sidewalks and highways. Tonight, we are going to push that intuition until it breaks. And if you enjoy having your brain pleasantly broken by the universe, tap like and subscribe so we can explore more of it together. Let us start on solid ground. You already know what a short walk feels like. A couple of blocks, a few hundred meters, maybe a kilometer or two. You know how long that takes, how it feels in your legs, how far the horizon looks when you stand in an open field. A few kilometers by car is nothing. It is a school run, a quick errand, the distance you barely register on a map. Stretch that to dozens of kilometers and it still feels familiar. A town 30 kilometers away is an easy drive. You imagine traffic lights, gas stations, maybe a stretch of empty highway. A couple of 100 kilometers is a weekend trip. You fill the tank, grab snacks, cue a playlist, and endure the slow shrink of your home city in the rearview mirror. These distances are folded into your life. You have lived them. Now scale up to a whole continent. The distance from New York to Los Angeles is roughly 4,500 kilometers. That is a 5-hour flight. You can imagine boarding the plane, feeling the hours blur as the scenery below changes from city grids to plains to mountains to ocean. 4,500 kilometers is a lot, but you have a story to hang on it. You know people who have done it. Maybe you have done it yourself. The Earth itself is about 40,000 kilometers around at the equator. That sounds huge, but we know it is crossable. Sailing ships did it over months. Modern jets can, in principle, circle the globe in under 2 days of continuous flight. You cannot walk it, but you can imagine a chain of flights and ships that would take you around this entire world. From our perspective, standing on its surface, Earth is large but not unimaginable. It is finite, conquerable. Now we leave that comfort zone. The average distance from Earth to the Moon is about 384,000 kilometers. Suddenly the map in your head fails. This is not a longer road trip or a more complicated flight. There is no highway, no scenery, no familiar landmarks. It is pure distance across a black vacuum. 384,000 kilometers is almost 10 times all the way around Earth. The Apollo astronauts crossed that gulf in about 3 days. Their spacecraft reached speeds of around 11 kilometers per second. That is about 40,000 kilometers per hour, roughly 400 times faster than a car on the highway. Imagine driving 400 times faster than you ever have for 3 days straight, and you still only just make it to the Moon. That is our nearest neighbor, the one you can see with your naked eye, with craters visible in backyard telescopes. From Earth, the Moon looks close enough to touch, a bright coin in the sky. The fact that it takes 3 days of sustained rocket-powered fall through space to reach it should make you suspicious of your own instincts. If the first step out from Earth already demands 3 days at 11 kilometers per second, what happens when we take the next step? The distance from Earth to the Sun is about 150 million kilometers. Try to imagine driving that. Your brain probably just shrugs. 150 million. It is a number you might hear in the context of money or population, but not distance. There is nothing in your daily life that uses this scale. It is beyond roads, beyond maps, beyond anything your ancestors ever had to care about. Take the Apollo spacecraft and point it at the Sun. At 11 kilometers per second, it would need roughly 160 days to reach the Sun's distance. More than 5 months of continuous travel through empty space, at a speed that felt extreme even to test pilots and astronauts. And it still would not be enough to get you anywhere near the edge of the solar system. You might think the answer is simple: build something faster. The Parker Solar Probe is currently the fastest spacecraft humans have ever launched. When it swings close to the Sun and uses gravity to slingshot itself, it reaches speeds of around 192 kilometers per second. That is about 17 times faster than Apollo. Numbers like that almost stop sounding real. Yet even at this astonishing speed, the probe still takes months to complete its tight, looping orbits around the Sun. Think about what that means. Our nearest star, the one that dominates our sky and powers our climate, is so far away that even with our fastest machine, ripping through space at nearly 200 kilometers every second, it takes months to dance around it. The Sun feels immediate. We see it every day. We feel its warmth on our skin. But in terms of raw distance, it is remote in a way our senses cannot capture. Now take another step. The next nearest star beyond the Sun, Proxima Centauri, is about 266,000 times farther away than the Sun is from Earth. Multiply that already absurd 150 million kilometers by hundreds of thousands. The numbers swell into ranges that are not just hard to picture, they are impossible to picture. At this point, using kilometers starts to feel like counting grains of sand to measure a beach. Technically correct, practically useless. This is the moment astronomers hit a wall. It is not that they dislike kilometers. Kilometers work beautifully for building roads, planning flights, and mapping planets. The problem is that when you step from planets to stars, the numbers inflate so violently that they stop meaning anything to a human mind. You can write them down, you can plug them into equations, you cannot really feel them. So the question becomes unavoidable. If ordinary units break at the scale of the cosmos, what comes next? What kind of measuring stick makes sense when the gaps between stars are hundreds of thousands of times the distance from Earth to the Sun? To answer that, scientists did something clever. They stopped using things humans had built as their ruler. They turned to the universe's own speed limit and let light itself define the unit. Once you realize that kilometers fall apart between stars, the obvious next question appears. What do we use instead? We need a ruler that is big enough to handle the cosmos, yet still tied to something physical and real. Not an arbitrary number humans invented, but a built-in feature of the universe itself. That is why astronomers reached for light. Light is not just bright, it is fast in a way that breaks your intuition. In a vacuum, light travels at about 300,000 kilometers per second. Every single second, it covers 300,000 kilometers. Imagine anything else doing that. In 1 second at that speed, you could go around Earth more than 7 times. In the time it takes you to snap your fingers, light could lap the planet over and over again. Nothing outruns this. This is not an engineering limit we simply have not cracked yet. According to our best physics, it is a hard cosmic speed limit. No signal, no particle, no information moves faster through space than light. You can build faster cars, faster planes, even faster spacecraft. But as you push closer to light speed, the universe itself starts pushing back. Later we will see how. For now, all we need is one fact. Light is the absolute champion of motion. For a long time, people assumed that champion was instant. You open your eyes and you see the world. When you light a candle, the room seems bright immediately. There is no sense of delay. So for centuries it felt natural to think that light simply appears, with no travel time at all. In the 1600s, a Danish astronomer named Ole Romer found evidence that this instinct was wrong. He studied the moons of Jupiter, especially one called Io, which regularly ducks behind the planet and reappears. These eclipses act like a natural clock, but Romer noticed that the timing of these events shifted depending on where Earth was in its orbit. When Earth was closer to Jupiter, the eclipses of Io seemed to happen earlier than expected. When Earth was farther away, they seemed to happen late. The moons themselves were not misbehaving. The clock was fine. What changed was the distance their light had to cross to reach Romer's telescope. He realized the only way to explain the pattern was if light needed time to travel those different distances. From this, Romer estimated how long light takes to cross the diameter of Earth's orbit. His numbers were not perfect, because nobody at the time knew the orbit's exact size. But the key idea landed. Light does not teleport, it has a finite speed. Since then, we have measured that speed with extreme precision. Modern experiments use lasers bouncing between mirrors, atomic clocks measuring tiny intervals of time, and clever setups that remove as many sources of error as possible. The result is that we know the speed of light better than almost any other number in physics. It is very close to 300,000 kilometers per second, and it stays the same no matter where you are or how you are moving. That constancy is what makes light such a good ruler. If light always moves through empty space at the same speed, you can use that speed to define a standard distance. Imagine saying the following: take light, let it run at full speed for 1 second, and call that distance 1 light second. Now let it run for a minute. That is 60 light seconds. Let it run for an hour. 60 minutes makes 3,600 light seconds. You can keep stacking those intervals. A full day is 24 hours, so 1 light day is 86,400 light seconds. A year is 365 days, which is 31,536,000 light seconds. Every one of those seconds, light is racing along at 300,000 kilometers. To work out how far it gets in a year, you simply multiply. Take 300,000 kilometers per second, multiply by 60 seconds per minute, multiply by 60 minutes per hour, multiply by 24 hours per day, multiply by 365 days per year. The final number is about 9.46 trillion kilometers. That distance is what we call 1 light year. Not a year of time, but a year of travel for light. A light year is how far a beam of light moves in 1 Earth year while sprinting at the universe's top speed. Roughly 9.46 trillion kilometers, which you will often see written as 9.46 followed by 12 zeros. On paper, this is tidy. It is just speed times time. In reality, your brain quietly rebels. Remember, 1 kilometer is a walk of around 10 minutes at a relaxed pace. It is a trip to the corner shop. A light year is 9.46 trillion of those little walks laid end to end in a straight line through space. Astronomers adopted this unit for a simple reason. It compresses ridiculous kilometer counts into numbers you can compare. Saying that Proxima Centauri is about 4.24 light-years away is much easier than saying it is roughly 40 trillion, 140 billion kilometers away. Light-years turn walls of digits into something you can at least talk about. But even with this new ruler, a problem remains. Your brain never evolved to juggle trillions. We toss around words like million, billion, and trillion, but we are terrible at feeling the gap between them. If we are going to understand what 1 light-year means, we need to get a grip on those giant numbers first. And that is where things start to get really uncomfortable. To understand 1 light-year, we first have to understand a trillion. And the truth is, almost nobody does. We use the word all the time. Government budgets in the trillions, national debts in the trillions, global markets worth trillions. It all blurs into one big category in your head called very large number. But million, billion, and trillion are not neighbours. They are different universes. Here is one of the simplest ways to feel the difference. Forget money. Think in seconds. Very ordinary. 1 second is a heartbeat, a blink, a click of a stopwatch. Now start counting. 1, 2, 3, and so on, saying one number every second. How long would it take you to reach these big milestones? 1 million seconds is about 11.5 days. If you started counting right now and somehow did not sleep, eat, or breathe wrong, you would reach 1 million in less than 2 weeks. That is long, but you can imagine it. 2 weeks is a holiday, a school break, a work project. Your brain has a place to file that time span. 1 billion seconds is something else entirely. 1 billion seconds is about 32 years. Not weeks, years. If you started counting one number per second on the day you were born and never stopped, you would hit 1 billion seconds sometime in your early 30s. 1 million seconds is a long weekend stretched out. 1 billion seconds is an entire generation. Already you can feel that the jump from million to billion is not just bigger, it is shocking. 1,000,000 seconds, 11 days. 1,000,000,000 seconds, 32 years. Same pattern, just adding 3 zeros. Yet the experience of that time could not be more different. Now push one step further. 1,000,000,000,000 seconds. Keep the same rule, one number every second. How long does it take? About 31,700 years. You heard that right. Not centuries, millennia. To put that in context, agriculture, the whole business of planting crops and staying in one place, is only about 10,000 years old. The first cities, writing systems, and organized states are roughly 5,000 years old. The pyramids are around 4,500 years old. The entire span of recorded human history fits into the last 5,000 years or so. If you had started counting to 1,000,000,000,000 seconds just before any of that happened, just before the first farms, before the first cities, before writing, before every empire you have ever heard of, you would still be counting today. You would have counted through the rise and fall of Egypt, Greece, Rome, every dynasty in China, the spread of every religion, every scientific revolution, the industrial age, the digital age, everything, and you would not even be done. That is what 1,000,000,000,000 looks like when you trade dollars for seconds. It is not simply a big number, it is a scale that stretches beyond history itself. And 1 light year is 9.46 trillion kilometers. Each of those kilometers is a real distance, about the amount you can walk in 10 to 12 minutes at a comfortable pace. A stroll to the local shop, a loop around your neighborhood. Picture that familiar kilometer as a single tile on a cosmic floor. Now imagine laying down 9.46 trillion of those tiles, edge to edge, in a straight line through space. You can say the number out loud. 9.46 trillion. You can write it. 9.46 followed by 12 zeros. You can feed it to a calculator. But try to feel it. Try to imagine walking those kilometers one by one. After the first 1,000, your legs ache. After the first 1,000,000, your brain taps out. After the first 1,000,000,000, you are so far beyond any human experience that the words lose their grip. After 9.46 trillion, we are not even in the same mental universe anymore. This is the core problem. Our brains evolved to count berries, people, tools, days. We are good at estimating a few, a handful, a dozen, maybe 100. We can work with 1,000 if we concentrate. Beyond that, we start leaning on symbols instead of intuition. 1,000,000 becomes a sound that means a lot. 1,000,000,000 becomes a sound that means even more. 1,000,000,000,000 becomes a sound that might as well mean infinity. When astronomers say that a light year is 9.46 trillion kilometers, they are doing precise physics. Speed multiplied by time, no mystery. But when you hear that statement, your brain quietly files it in the same folder as infinite distance. The number is so far beyond your instincts that it might as well be magic. That is why simply giving the number is not enough. If all you hear is trillions of kilometers, you know it is big, but you do not feel anything. It is like reading the calorie count of a star, accurate but emotionally flat. To make light years meaningful, we need a different strategy. Instead of jumping straight to a year of light travel, we are going to climb there one step at a time, starting with something your brain can barely handle and then scaling up. We will begin with 1 light second, a distance already enormous by human standards. Then we will stack those seconds into minutes, hours, days, weeks, months, and only then into a full light year. At each step, we will tie the distance to something concrete: the Moon, the Sun, Mars, Saturn, the far edge of the region Voyager has reached. By the time we arrive back at that 9.46 trillion kilometer figure, it will no longer just be a wall of digits. It will be the top rung of a ladder you have climbed yourself, rung by rung, with your intuition stretched at every step. To make light years feel less like magic and more like distance, we need a staircase. Not a jump from your front door to the next galaxy, but a series of steps where each one stretches your intuition just a little more. That staircase starts with the simplest possible unit based on light: 1 light second. A light second is exactly what it sounds like. the distance light travels in 1 second at its top speed in a vacuum. Since light moves at about 300,000 kilometers per second, 1 light second is 300,000 kilometers. On Earth, that number already dwarfs anything you will ever travel. For comparison, the average distance from Earth to the Moon is about 384,000 kilometers. That means 1 light second is roughly the distance from Earth to the Moon and most of the way back. In the time it takes you to say the word one, a photon could leave Earth, cross the empty space to the Moon, bounce off an imaginary mirror, and get 3/4 of the way home again, all in a single second. You can hear this in the recordings from the Apollo missions. When astronauts on the Moon spoke to Mission Control in Houston, there was always a pause. Their words, sent as radio waves traveling at the speed of light, took about 1.3 seconds to reach Earth. The reply took another 1.3 seconds to go back. Every exchange carried an almost 3-second rhythm gap, a tiny human-level reminder that even light needs time. Now stack those seconds. 60 light seconds make 1 light minute. Multiply 300,000 kilometers by 60, and you get around 18 million kilometers. That is already a distance so absurd that cars and planes are meaningless metaphors. You have stepped into a realm where only spacecraft and numbers live. Earth orbits the Sun at a distance of about 150 million kilometers. In terms of light, that is roughly 8 and a bit light minutes. When you look at the Sun, you are seeing it not as it is now, but as it was about 8 minutes and 20 seconds ago. If the Sun could somehow snap off like a light bulb, the sky would stay bright for more than 8 minutes before the darkness arrived. The information about what happened has to cross those light minutes first. That same delay is what makes Mars feel far away, even though it is right next door in astronomical terms. The distance between Earth and Mars is not fixed. It changes as both planets move in their orbits. At the very closest, they are separated by about 32 million kilometers, roughly 2 light minutes. At the farthest, when they are on opposite sides of the Sun, the gap grows to about 400 million kilometers, about 22 light minutes. When engineers at NASA drive a rover on Mars, they cannot use a joystick and react in real time. If they send a command now, and Mars happens to be far away in its orbit, that command might not arrive for 20 minutes. The rover carries out the instructions, then spends another 20 minutes shouting its status back across space. A simple problem that would take seconds to fix with a remote-controlled car on Earth can stretch to an hour of delays on Mars. Take another step up. 60 light minutes make 1 light hour. Multiply those 18 million kilometers again, and you are now talking about more than 1 billion kilometers. Distances this big start to encompass the outer planets. At its closest, Saturn sits about 1.2 light hours away from Earth. When the Cassini spacecraft was orbiting Saturn, every photo it took, every measurement it sent, had to cross that gulf. Cassini would capture an image, compress it into a radio signal, and beam it home. Over an hour later, that data would finally arrive at a dish on Earth. If something went wrong at Saturn, controllers would hear about it an hour after it started, and any fix they sent back would take another hour to arrive. In effect, the spacecraft had to be trusted to look after itself. Now scale up again. 24 light hours make 1 light day. Light day sounds poetic, but the number behind it is ruthless. 1 light day is about 25,900,000,000 kilometers. Voyager 1, launched in 1977, has been racing outward from Earth for nearly half a century. Its speed is around 17 kilometers per second, a pace that would zip you across an entire continent in a few minutes. Yet after all those decades of uninterrupted flight through the vacuum of space, Voyager 1 is only about 1 light day from the Sun. The most distant human-made object has not yet travelled a distance that light covers between sunrise and the following sunrise. 7 light days make a light week. At that range, you are far beyond the orbits of the planets, out in the deep dark where the Sun would shine as a brilliant star rather than a blinding disk. The warmth and brightness that feel overwhelming on Earth would have faded to a hard point of light among many others. Extend that to roughly 30 light days, and you get something like a light month. From that vantage point, the entire solar system would shrink into a tiny glow around a single star. Jupiter, Saturn, all the inner planets, the asteroid belt, the scattered comets, everything that seems spacious and spread out when you look at diagrams would be squeezed into a pinprick of light. You could point a telescope back toward home, and the sun would not look particularly special, just one bright star among thousands. Now take all those steps together. A light second, 300,000 kilometers. 60 of those give a light minute. 60 light minutes give a light hour. 24 light hours give a light day. 7 light days give a light week. Around 30 light days give a light month. 12 light months give a light year. At each stage you have multiplied by a number that your brain can barely track. 60, then 60, then 24, then 7, then 30, then 12. By the time you reach a full year of light travel, you are back at that 9.46 trillion kilometer monster. But now it is not a random huge value. It is the top of a staircase that began with 1 second of motion and climbed steadily outward, past the Moon, past Mars, past Saturn, past Voyager, into the quiet black between the stars. Light years are still difficult to picture. They always will be. But once you have walked this ladder from light seconds to light years, you have at least one precious thing, a sense of how wildly everything scales. And you are finally ready to talk about the stars next door, and why even our closest cosmic neighbours might as well be on the other side of eternity. Now that you have climbed from light seconds to light years, we can finally ask the question everyone secretly cares about. Can we actually go to the stars? Because if the distances are just big numbers on paper, it is interesting. If those distances lock us in our own solar system, it becomes personal. Meet our closest real neighbour, Proxima Centauri. It is the nearest star beyond the Sun, at about 4.24 light-years away. On the human scale, that sounds almost friendly, 4 and a bit. You could drive that many kilometres to visit a friend in another town. But remember what sits behind each light-year. 9.46 trillion kilometres. 4.24 of those is roughly 40 trillion 140 billion kilometres. Proxima Centauri belongs to the Alpha Centauri system, a gravitational dance of 3 stars. 2 of them, Alpha Centauri A and Alpha Centauri B, are sun-like stars, orbiting each other in a slow loop that takes almost 80 years. If you could float nearby, you would see 2 suns tracing wide arcs in the sky. Proxima is the runt of the family, a small red dwarf with about 1/8 the mass of the Sun and a fraction of its brightness, drifting farther out. You cannot see Proxima with the naked eye at all. Our nearest stellar neighbour is invisible unless you bring a telescope. So how long would it take to get there with our current best hardware? Take the Parker Solar Probe, the speed champion of human engineering. At its peak near the Sun, it moves at about 192 kilometers per second. That is so fast, it crosses the distance from New York to Los Angeles in less than a minute. At that speed, you would expect the universe to start feeling smaller. Now give that speed to an imaginary starship pointed at Proxima Centauri, and ask how long the journey takes. The answer is about 6,800 years. Not 6 days or 6 months or even 6 centuries, 6,800 years, longer than all of recorded human history. If you had launched such a mission when humans first invented writing, the ship would still be crawling through interstellar space today, with thousands of years left to go. That is our fastest spacecraft. Not a comfortable generation ship with gardens and artificial gravity, an instrument platform with a tiny amount of shielding designed for a very specific mission. Turning that into a human carrying vessel makes everything harder. You have to add life support, radiation protection, food, water, air, recycling systems, backup systems for the backup systems. Every extra kilogram you add makes it harder to accelerate. To make interstellar travel feel even slightly practical, people dream of much higher speeds. Concepts like fusion rockets, antimatter drives, or beamed propulsion aim for 10% or 20% of light speed. At 10% of light speed, you could reach Proxima Centauri in around 42 years. That is still longer than most careers, but it now fits inside a human life. In theory, you could launch as a young adult and arrive as an older one. One of the boldest proposals in this direction is Breakthrough Starshot. The idea is to build spacecraft that are not big ships at all, but tiny chips with sails. You take something about the mass of a paperclip, attach an ultra-thin reflective sail only a few atoms thick, then fire a massive array of ground-based lasers at it. The light from the lasers pushes on the sail, and because the craft is so light, it could be accelerated to around 20% of light speed. At that speed, 60,000 kilometers per second, a probe could reach Proxima Centauri in about 20 years. Add just over 4 years for its signal to travel back at light speed, and you might get the first close-up data from another star system 24 years after launch. That is an astonishing thought. Send a gram-sized robot and get postcards from another sun within a single human lifetime. The catch is in the details. You would need laser power on the order of 100 gigawatts, roughly what 100 large nuclear power plants produce, focused into a beam a few kilometers wide and kept perfectly locked on a wafer-sized sail for minutes. The sail must survive being hammered by that beam without tearing or evaporating. It then has to withstand decades of crossing interstellar space, while slamming into dust grains at tens of thousands of kilometers per second. At those speeds, a particle smaller than a grain of sand is a bullet. A collision releases energy like an explosive, shredding unprotected material. So you add shielding. That makes the craft heavier. Heavier craft need more laser power, which means more cost, more infrastructure, more engineering headaches. Then there is communication. When the probe finally screams past Proxima Centauri, it cannot slow down. It simply flashes through the system at a fraction of light speed, with maybe a few hours in the sweet spot where it can take detailed pictures. It has to compress those pictures and measurements, aim a tiny transmitter back toward a distant Earth, and shout across 4.24 light-years with barely any power. We would be listening for a whisper from a chip, buried in the noise of the galaxy. So while Starshot is rooted in real physics, it lives on the extreme edge of what might be feasible. It is not a plan we can execute tomorrow. It is a sketch of what could be possible if we are willing to build planet-scale engineering projects to push gram-sized explorers into the dark. And remember, this is all for the closest star. Most stars are much farther away. Many of the interesting exoplanets we have discovered are dozens or hundreds of light-years distant. Even at Starshot speeds, those would be journeys lasting centuries. Human crews would need multi-generational ships, entire moving ecosystems and cultures that drift between the stars for lifetimes. Our local stellar neighborhood drives the point home. Within about 20 light-years of Earth, there are roughly 130 star systems. Many are red dwarfs like Proxima Centauri. A few are more familiar, like Sirius, a bright white star with a dense white dwarf companion, or Barnard's star and Wolf 359. Small red dwarfs racing across the sky with high proper motion. Some of these stars are moving at over 100 kilometers per second relative to the Sun. That sounds incredibly fast until you compare it to the distances. Even a star screaming along at 100 kilometers per second is moving at only a tiny fraction of light speed. At that rate, it would still need tens of thousands of years to drift a single light-year. From our perspective, the stars are not just far apart, they are pinned in place by the sheer scale of the gaps between them. So when you hear 4 light-years, or 10 light-years, or 100 light-years, do not picture the comfortable units of road trips and airline tickets. Picture thousands of years at our current best speeds. Picture entire civilizations rising and falling, while a single mission crawls between 2 suns. The light-year is not just a handy unit, it is the first hint that there is a deeper barrier in the universe, one that has nothing to do with engineering skill and everything to do with the nature of space and time themselves. At this point, it is tempting to think the problem of distance has a simple answer. Just go faster. Build stronger rockets, better engines, more advanced spacecraft, and eventually those light years will shrink. After all, that is how we solve distance on Earth. We went from walking to horses to trains to jets, so why not do the same thing between stars? The trouble is that the universe lets you do that for a while, then quietly changes the rules. At low speeds, the world behaves in a very straightforward way. If you're on a train moving 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, someone standing beside the track sees the ball moving at about 70 kilometers per hour. Your speed plus the ball's speed. Common sense. For centuries, people assumed this rule worked for everything. Speeds add. Simple. Then physicists started looking closely at light. No matter how they measured it, no matter whether the source was moving or the observer was moving, they kept getting the same answer. In empty space, light always travels at about 300,000 kilometers per second. Imagine a spaceship flying at half the speed of light relative to Earth. Inside, an astronaut shines a flashlight forward. You might expect that someone watching from Earth would see the beam racing ahead at 1.5 times light speed. Half from the ship, 1 from the light itself. That would match the train and ball logic. But that is not what nature does. Both the astronaut on the ship and the observer on Earth measure the speed of the beam and get the same value. Light moves away at 300,000 kilometers per second, according to both of them. The universe refuses to let light be any faster or slower, so something else has to give. Einstein's insight in the early 20th century was that what gives is not the speed of light, it is space and time. To keep the speed of light fixed for everyone, the universe stretches and squeezes measurements of distance and duration depending on how you move. At everyday speeds, you never notice this. The effects are microscopic. As you approach light speed, those effects grow enormous. If you move very fast compared to someone else, time literally passes differently for you. From the perspective of a stationary observer, your clock runs slow. Your heart beats more slowly. Your thoughts unfold more slowly. Your aging slows. At the same time, distances in the direction you travel appear shorter to you than they do to someone watching from the outside. Space and time flex to keep light speed constant. This sounds like science fiction, but it is measured fact. In particle accelerators, tiny particles are pushed to speeds incredibly close to light speed. Many of these particles are unstable and decay after a short time when they sit still. When they are moving near light speed, they live much longer. Their internal clocks are slowed compared to clocks in the lab. High-energy particles from space slam into the upper atmosphere and create particles called muons. Muons decay in about 2 millionths of a second in their own rest frame. Even moving at high speed, that lifetime is so short that they should never make it to the ground before decaying. Yet we detect muons at the surface of Earth all the time. From our perspective, time dilation has stretched their short lives long enough for them to survive the journey through the air. We see the same effect with technology we use every day. The Global Positioning System, often called GPS, relies on satellites orbiting Earth with precise atomic clocks on board. Those satellites move quickly and sit higher in Earth's gravitational field, both of which affect the flow of time. Their clocks tick at slightly different rates than identical clocks on the ground. If engineers did not correct for this relativistic time dilation, your navigation app would drift wrong by several kilometers in just a few hours. The fact that your phone can tell you where you are is silent proof that Einstein's strange ideas are true. As your speed approaches the speed of light, time dilation becomes extreme. From the viewpoint of an observer at rest, it becomes harder and harder to push you faster. Your energy and inertia increase in such a way that you need more and more energy to gain smaller and smaller bits of speed. To actually reach light speed, a massive object would require infinite energy. The universe does not have infinite energy to give, so anything with mass is forever locked below that limit. Massless particles like photons have a different deal. They are born moving at light speed, and they never slow down. They do not need infinite energy to reach that speed because they never had to accelerate up to it in the first place. For them, traveling at light speed is simply existing. For everything else, it is a wall. So what does this cosmic speed limit do to our dreams of visiting the stars? It creates a strange compromise. You can never outrun light, but you can get close enough that your personal experience of time changes dramatically. From your perspective on board a near light-speed ship, journeys that take decades or centuries as measured from Earth might take only months or years. In other words, high-speed interstellar travel is also time travel into the future. Imagine a star 10 light-years away. From the point of view of Earth, light takes 10 years to reach that star and another 10 years to come back. A round trip at light speed would take 20 years. Now suppose you have a spacecraft that can cruise at 99.9% of light speed. You accelerate up to that velocity, coast to the star, turn around and come home. Observers on Earth watch the journey and see about 20 years pass between departure and return. For them, the math is simple. You covered 10 light years out and 10 light years back at just under light speed. For you aboard the ship, time dilation kicks in hard. At 99.9% of light speed, time on board runs about 22 times slower than on Earth. So while 20 years pass on Earth, you experience only around 11 months. From your point of view, you go on an extended trip, maybe less than a year of subjective time, and return home. When you land, everyone you left behind is 20 years older. Children are now adults, young people have grey hair. The music, slang and politics you remember belong to a different era. You have leapt forward in time compared to everyone else. Push the speed even closer to light and the effect grows stronger. Imagine a journey to a star 100 light years away and back, at a speed where the time dilation factor is so extreme that 200 years pass on Earth, while only a few years pass for you. You would leave in 1 century and return in another, stepping out of your ship into a world as different from your starting point as the modern world is from the days before electricity. This is not fantasy. The equations of relativity predict it, and our experiments support those equations. Near light speed travel, if we can ever engineer it, is a one-way ticket to someone else's future. You can go out there and experience a short adventure while centuries pass back home, but you cannot come back to yesterday. Faster-than-light return trips are forbidden by the same physics that gives you the effect in the first place. The speed of light, then, is more than a big number on a datasheet. It is the rule that shapes every possible path between stars. It tells us that there is no technological trick that will let a ship race to Proxima Centauri in a week and back by the weekend. It limits how quickly civilizations can talk, travel, trade, or meet. And it turns every ambitious trip between the stars into a story not only about distance, but about time, and about what it means to leave a world knowing that when you return, if you ever do, it will no longer be the world you left. The moment you accept that light has a speed and that speed has a hard limit, something subtle but profound happens. Distance and time fuse. You can no longer talk about how far away something is without also talking about how long its light has been travelling. Every time you look up, you are not seeing the universe as it is. You are seeing a layered fossil record of how it used to be. The night sky is not a picture, it is a time machine. You already met the first hint of this earlier. Light from the sun takes a little over 8 minutes to reach Earth. So when you see the sun in the sky, you are seeing it as it was about 8 minutes ago. If the sun could vanish in an instant, the blue sky and daylight would persist for 8 minutes more. Earth does not know what is happening at the sun right now. It only knows what the light tells it, and the light is always a few minutes behind. The moon is closer, so its delay is shorter. Light takes about 1.3 seconds to travel from the moon to Earth. When Apollo astronauts spoke from the lunar surface, every word took that 1.3 second journey as a radio wave at light speed. Mission Control replied, another 1.3 seconds passed. That is why you hear that odd gap in old recordings, a built-in pause that is really empty space being crossed. Now extend that idea to the stars. Sirius, the brightest star in our night sky, is about 8.6 light-years away. When you look at Sirius tonight, you are seeing it as it was 8.6 years ago. If you are 20 years old, this is Sirius from when you were about 11. If you are 40, you are seeing Sirius from your early 30s. The real star, right now, is 8.5 years ahead of what you can see. Vega, another bright star, sits about 25 light-years away. If you are 25 years old and you look at Vega, the light hitting your eyes left that star the year you were born. When that photon began its journey, you did not exist yet. Your parents may have been children or teenagers, looking up at Vega and seeing light from an even earlier era. The sky is full of delayed broadcasts like this, messages sent long before you arrived. Then comes Betelgeuse, the red supergiant marking the shoulder of Orion. It is about 550 light-years away. The reddish glow you see on a winter night began its trip toward Earth around the year 1474. Europe was in the middle of the Renaissance. Printing presses were new. Leonardo da Vinci was a young man. Michelangelo was not yet born. Entire empires have risen and fallen while those photons coasted through space. Betelgeuse is also a star near the end of its life. Massive stars burn through their fuel quickly and die young in spectacular supernova explosions. Astronomers believe Betelgeuse will explode sometime in the next 100,000 years, a blink in stellar terms. When it does, it will shine almost as bright as the full moon and be visible even during the day. Here is the eerie part. Betelgeuse might have already exploded. The blast could have happened hundreds of years ago. If that is true, the light from that event is still on its way to us, crawling across those 550 light-years. We would not know. We would still see a calm red star in our sky, while in reality that star is gone, replaced by an expanding cloud of glowing debris. In a sense, we would be looking at a ghost. Polaris, the North Star, sits about 445 light-years away. When its current light began travelling toward Earth, the first permanent English colonies in North America did not exist yet. Jamestown would not be founded for another decade or so. Shakespeare was alive and writing, but had not yet created many of his most famous plays. Modern nation-states and technologies were still far in the future. Yet tonight, photons that left Polaris in that world enter your eyes. You are literally seeing a different century. Within about 20 light-years of Earth, there are around 130 known star systems. Some are single stars like the Sun, others are binaries, two stars orbiting a common centre. A few are triple systems, like Alpha Centauri, where two Sun-like stars orbit each other, while a smaller red dwarf loops farther out. Barnard's star, around 6 light-years away, is a dim red dwarf famous for its motion. Against the background of other stars, it creeps noticeably over decades. Astronomers call this proper motion. Among nearby stars, Barnard's star has the largest apparent motion on the sky. Over thousands of years, its position noticeably shifts. In about 10,000 years, it will be closer to us than Proxima Centauri is now, becoming our new nearest neighbour. Even so, it will still be nearly 4 light-years away. Wolf 359, about 7.9 light-years distant, is another small red dwarf with a high space velocity. It is racing through our region of the galaxy at about 119 kilometers per second relative to the Sun. That sounds extreme, yet it is still moving at only a tiny fraction of light speed. Even at that pace, it would need tens of thousands of years to travel a single light-year. Nearby stars are not just far away, they are glued into place by the sheer size of the gaps between them. Sirius itself is not solitary. It is a binary system. Sirius A is a hot white star, a bit more massive than the Sun. Its companion, Sirius B, is a white dwarf, the collapsed core of a once normal star that has exhausted its nuclear fuel. A white dwarf packs roughly the mass of the Sun into a sphere about the size of Earth. A teaspoon of its material would weigh several tons at Earth gravity. The two stars orbit each other every 50 years, locked in a tight gravitational partnership. Zoom out farther, and our sense of scale takes another hit. The Milky Way is a barred spiral galaxy, containing perhaps 200 to 300 billion stars. The exact number is hard to pin down because we are inside the system, looking through clouds of gas and dust that block our view. From our position, we are like someone standing in a forest trying to count trees through the branches. Our Sun sits in one of the spiral arms, about 26,000 light-years from the galactic centre. Any light we manage to capture from that centre, at radio or infrared wavelengths that can pierce the dust, left 26,000 years ago. At that time, humans were hunter-gatherers in the late Stone Age. There were no farms, no cities, no writing. People moved with the seasons, following herds and wild plants. Everything we call civilization has unfolded while that light was in transit. The Milky Way is roughly 100,000 light-years across. If you could somehow ride a photon from one edge of the disk to the other, the trip would take 100,000 years. Modern humans as a species are only about 300,000 years old. So a single crossing of our galaxy at light speed spans roughly a third of our entire existence. Meanwhile, the Sun is not sitting still. It orbits the galactic centre at about 230 kilometers per second. At that speed, it completes one full lap in roughly 225 to 250 million years. The last time the Sun was in its current position on that orbit, dinosaurs were just beginning to appear on Earth. Since then, they evolved into giants, ruled the planet for over 160 million years, were wiped out, mammals diversified, apes appeared, humans evolved, and the Sun has only now returned to roughly the same galactic longitude. And beyond our galaxy, the universe keeps going. The region we can, in principle, observe, set by how far light has had time to travel since the Big Bang, extends about 46 billion light-years in every direction. That makes the observable universe about 93 billion light-years across. Inside that sphere are estimated to be around 2 trillion galaxies, collectively containing something like 200 billion trillion stars. When you put this all together, the night sky turns into a stack of distances and eras. Sirius shows you a decade-old past. Vega shows you birth year light. Betelgeuse shows you the Renaissance. Polaris shows you the age of Shakespeare. The galactic centre shows you humans before civilization. Distant galaxies show you a universe that was far younger than it is now. Every light year is both a stretch of almost unimaginable distance and a slice of time. When you look up, you are seeing not a single moment, but a layered history written in photons. You are standing on a small world, orbiting an ordinary star, inside one galaxy among trillions, watching ancient messages arrive from across space and time. And that deep connection between distance and age is the key to understanding why the universe looks the way it does, and why, at the largest scales, it sometimes feels eerily quiet. So far, light years have mostly been an abstract measuring stick, useful for making sense of stars and galaxies, brutal for travel, poetic for looking back in time. Now it is time to ask a more human question. What happens to relationships when distance is measured in light years? To friendships, to families, to entire civilizations? First, we need a reason to care about distant stars at all. For most of human history, stars were just lights. Beautiful, mysterious, but not destinations. That changed in the 1990s. In 1992, astronomers found the first planets orbiting another star, a pulsar. In 1995, they found the first planet around a normal Sun-like star. Since then, the floodgates have opened. As of the mid-2020s, we have confirmed over 5,000 exoplanets, with thousands more candidates waiting in the data. We now know that planets are not rare jewels, they are common. Many stars have them. Some of those planets are rocky. Some lie in so-called habitable zones, where temperatures might allow liquid water. In other words, the universe is not just full of stars, it is full of worlds. One system in particular captured the imagination of scientists and the public, TRAPPIST-1, a small red dwarf star about 40 light-years away, with 7 Earth-sized planets packed tightly around it. 3 of those planets orbit in the habitable zone, where starlight is not too strong and not too weak. On paper, they look like candidates for oceans, atmospheres, maybe even life. TRAPPIST-1 also tells us something about the galaxy. It is a red dwarf. Stars like that are the most common kind in the Milky Way, making up roughly 70% of all stars. If a modest little red star can host a rich family of rocky worlds, it hints that such systems might be everywhere. The raw material for habitable planets could be the rule, not the exception. So the dream emerges: colonies under other suns, human settlements on planets orbiting distant stars, maybe a base on a world around Proxima Centauri, maybe city lights glimmering on a TRAPPIST-1 planet. The technology is hard, the physics is unforgiving. But suppose, just for a moment, that we solve the engineering, that we find a way to send people there. What happens then? This is where light years stop being just geometry and turn into social gravity, because even if you could travel there, you cannot outrun the speed of light. Communication would always crawl. We have already had a taste of this with Mars. As we saw earlier, the distance between Earth and Mars ranges from about 2 light minutes at its closest to around 22 light minutes at its farthest. That creates communication delays of between 4 and 44 minutes for a full back and forth. You cannot joystick a rover across a Martian landscape. You send a batch of commands, wait tens of minutes to see what happened, then send another batch. Every interaction is slow, careful, one step removed. Now stretch that idea to Proxima Centauri at 4.24 light-years away. Imagine a human settlement on a planet there. You send a message asking how the first harvest went. That message is not an email. It is a beam of radio waves or laser light slogging through 4.24 years of empty space. They receive it 4 years and a bit later, write a reply, and fire it back. You receive their answer more than 8 years after you asked. Think about what that does to everything we take for granted in communication. You ask how your child is doing. By the time you get the answer, that child is in a completely different life stage. You ask about a crisis. By the time the reply arrives, the crisis is long over, one way or another. You give advice, and it lands years too late. Now imagine trying to govern a colony with that delay. Laws sent from Earth would arrive years out of date. Policies would be based on old information about a society that has been changing the entire time. By the moment a message from Earth reaches Proxima, the political situation at home might have flipped completely. New leaders, new priorities, maybe even a different system of government. Reverse the direction, and it is no better. The colony sends a plea for help. Food shortages, a disease outbreak, a diplomatic crisis with a rival settlement on another world in the same system. By the time Earth receives the message, the emergency is history. Whatever help Earth sends is essentially a time capsule of intentions aimed at a past that no longer exists. At 10 light-years away, the round-trip communication time stretches to about 20 years. You could ask a question in your 20s and, if you are lucky, hear the answer in your 40s. At 100 light-years, a simple exchange takes 2 centuries. You send a greeting. Your great-great-grandchildren might hear the reply. If you are sending culture, science, art, you are no longer having a conversation. You are engaging in a kind of slow-motion archaeology. This means any real colony beyond our solar system cannot be tightly controlled from Earth. It has to be self-governing. Everyday decisions about resources, conflicts, emergencies and culture cannot wait 10 or 20 years for feedback. The people living under another sun would develop their own habits, laws, customs and identity. By the time a message from Earth arrives telling them how to handle a problem, they will have already invented their own solution. Over generations, those differences would deepen. Language might drift. Traditions would evolve to match their environment. Holidays would mark local events, like the day their first crops grew under a dim red star, or the day a storm nearly wiped out their habitats. Earth would slowly become a legend, the old world where their ancestors came from, far away and impossibly slow to answer. On the family level, the emotional cost is heavy. A parent who leaves for a nearby star and travels close to light speed might age only a few years during the trip, while decades pass at home. When they send messages back, each reply is a snapshot from years ago. Their relationships become a chain of letters stretching across time, each one arriving from a version of a person who no longer exists. This is the quiet cruelty of light years. They do not just make travel hard, they make togetherness fragile. They take the instant back and forth that defines human connection and stretch it until a conversation spans eras. If the galaxy is full of life, then in one sense that is wonderful. Yet in practice, every world that bears minds is likely to be a tiny island in a vast black ocean, shouting across distances so great that by the time any answer returns, the voices on both ends have already changed. Light years already feel cruel at the scale of stars. On the scale of the whole universe, they become something stranger. Not just markers of distance and time, but markers of what is reachable at all. Because while light races through space, space itself is doing something unexpected. It is stretching. Astronomers discovered that distant galaxies are not simply sitting there. When we measure the light from those galaxies, we find that almost all of them are redshifted, their light stretched to longer wavelengths. The simplest way to explain this is that the space between us and them has expanded during the light's journey. Imagine raisins in rising bread dough. The raisins are galaxies, the dough is space. As the dough expands, every raisin drifts away from every other one. On small scales, gravity completely overpowers this expansion. The space between you and your chair is not stretching. The distance between Earth and the Moon is not stretching. The solar system is held together tightly enough that cosmic expansion has no real effect. Even the Milky Way as a whole is held together by gravity, so its stars orbit normally, while space expands on much larger scales. Between galaxies that are far apart, though, the stretching of space becomes important. The farther away a galaxy is, the more space there is between us and it, and the more that space has expanded while light was in transit. To us, this shows up as a recession speed. Distant galaxies appear to be moving away. The more distant they are, the faster they recede. Here is the mind-bending part. For galaxies far enough away, the expansion of space makes the distance between us grow faster than light can cross it. This does not mean those galaxies are breaking the cosmic speed limit by racing through space faster than light. Locally, they are just sitting in their own patches of space, drifting a bit under gravity. It is the space in between that is stretching. The treadmill beneath our feet is running backward, faster than we can walk forward. This leads to the idea of a cosmic horizon. There is a distance beyond which light emitted right now will never reach us, no matter how long we wait. The expansion of space will always outrun that light, carrying its source farther and farther away. Even with perfect telescopes, even with infinite patience, the regions beyond that horizon are forever cut off. They are not simply unseen, they are in principle unseeable. The observable universe, the part we can in theory see, is already finite because the universe has a finite age. Light has had only about 13.8 billion years to travel, but the expansion adds another layer. Some regions that might once have been visible are now receding so fast that their future light is lost to us. The universe is larger than the sphere of what we can ever know. Now fold in the possibility of life. The universe contains perhaps 2 trillion galaxies. Each galaxy holds hundreds of billions of stars. Many of those stars have planets. Given how quickly life appeared on Earth once conditions were right, it feels reasonable to suspect that life may have formed elsewhere, perhaps often, perhaps with intelligence and technology many times. Yet when we listen, the universe seems quiet. Radio telescopes scan the sky, searching for narrow-band signals or artificial patterns. We see pulsars, quasars, natural radio noise, but no unambiguous sign of an alien broadcast. No obvious laser beacons, no galaxy-spanning engineering projects. Nothing that clearly says, we are here. This puzzle is known as the Fermi paradox. Given so many stars and so much time, where is everybody? One piece of the answer is simply scale. Our oldest radio transmissions have been leaking into space for about 100 years. Those signals travel at light speed, forming an expanding bubble around Earth with a radius of 100 light years. That sounds huge until you compare it to the Milky Way, which is about 100,000 light years across. Our radio bubble is a tiny sphere of influence inside a galaxy so vast that it is barely a pinprick. Within that bubble, there are perhaps a few thousand stars. Even there, picking up our signals is hard. Broadcasts spread out as they travel, their power diluted over an ever-growing sphere. By the time an old television signal reaches a nearby star, it is far weaker than the background noise of the cosmos. An alien civilization would need enormous antennas, pointed at exactly the right place, tuned to exactly the right frequency, at exactly the right time, just to notice a faint whisper from us. The reverse is true as well. If another civilization is broadcasting from 50 light-years away with roughly Earth-level technology, their accidental leakage would be almost impossible for us to detect. Even deliberate beacons are easy to miss if we are not looking in the right direction with the right instruments. Silence in our data does not mean silence in the galaxy. It might just mean the music is too far away and too faint. Then the light year does something more brutal. It stretches every attempted conversation into an epic. A star 50 light-years away sends a signal. We detect it, perhaps by luck. We answer. They do the same. A single exchange takes a century. 2 messages, 1 question and 1 reply. By the time that reply arrives, the people who sent the original question are likely gone. Governments have changed, technologies have shifted, cultures have evolved. The conversation becomes a chain of letters passed across generations. Now imagine that the average distance between technological civilizations is not 50 light-years, but hundreds or thousands. The galaxy is big enough for that to be entirely possible. At those ranges, the round-trip time for even a single exchange of information stretches to many thousands of years. Civilizations may rise and fall in less time. By the time one world hears the first hello from another, the senders might already be extinct. We would be reading a fossil record of minds that no longer exist. Combine this with cosmic expansion, and the picture becomes even more isolating. There are regions of the universe that no signal from us will ever reach, and from which no signal will ever reach us. There may be countless galaxies full of life beyond our cosmic horizon, each with its own dramas and discoveries, forever invisible and unreachable. From our vantage point, they might as well not exist. So we arrive at a melancholy possibility. The universe could be full of civilizations, each confined to its own little island of space and time. Each one broadcasts, listens, hopes, and then eventually fades, never knowing whether others did the same. The distances measured in light-years are not just big, they can be big enough to erase dialogue itself. And yet, there is a strange beauty hiding inside that loneliness. If contact is nearly impossible, then every civilization that does arise is uniquely precious. A local miracle, a one-time event in its own region of the cosmos. If we are the only technological species for dozens or hundreds of light-years around, then all the thinking, dreaming, creating and questioning that happens here is not just one more voice in a crowded choir. It might be the only song for a very long way. By now, the light year should feel less like a sci-fi buzzword and more like a quiet, stubborn fact of reality. It is the distance light travels in 1 year, about 9.46 trillion kilometers. It is the gap between us and our nearest stellar neighbors. It is the scale of our galaxy and the yardstick for the visible universe. But it is also something more human. It is a mirror that shows us who we are and where we fit in the story of the cosmos. Start with the humbling side. Everything you have ever known has happened on a world that is tiny compared to the Sun, which itself is an average star in a galaxy 100,000 light-years wide, in a universe filled with trillions of other galaxies. The nearest star beyond the Sun is over 4 light-years away. The Milky Way alone holds hundreds of billions of stars, each one separated by enormous distances. On those scales, a human life of 80 or 90 years is a flicker. A civilization lasting a few thousand years is the briefest of experiments. From far enough away, none of our dramas register. The rise and fall of empires, the drawing and redrawing of borders, the arguments that consume whole generations. All of it happens on one small rock orbiting a single star in a single galaxy. No distant galaxy pauses when we hold elections. No star trembles when we go to war. The universe goes on. Galaxies collide, stars are born and die, black holes grow, and none of it depends on us. That can feel crushing. If we are so small, do our choices matter at all? If our entire history is a thin scratch on the surface of cosmic time, does anything we do survive that perspective? The light year forces us to sit with that discomfort, to accept that the cosmos is not built to make humans feel important. It simply is, on scales that dwarf us. But there is another side. The very fact that we can think about light years at all is astonishing. We are collections of atoms assembled by blind physics into living systems that can step back and measure the universe that produced them. On a planet that orbits an ordinary star, life appeared, evolved, and eventually produced minds that built telescopes, wrote equations, and calculated the distances to other suns. Consider what it took to reach this point. Generations of curious people learned to track the motions of the stars, to build better instruments, to question old models, to test new ones. They watched Jupiter's moons blink in and out of shadow and realized light has a speed. They measured parallax shifts of nearby stars as Earth moved in its orbit and used geometry to find their distances. They examined the faint stretching of starlight and discovered that space itself is expanding. Each step was tiny on its own. Each insight was local. Together they formed a ladder from village skies to a universe 93 billion light-years wide. The light year is not just a number, it is the end result of centuries of humans insisting on understanding what they see. That stubborn curiosity is anything but insignificant. There is also a practical weight to all this. The speed of light and the distances involved set hard boundaries on what we can and cannot do. They tell us that travel to other stars will be slow, that communication will lag, that interstellar empires ruled from a single world are not realistic. They hint that we may be limited to robotic explorers beyond our own system, at least for a very long time. That limitation is not a punishment, it is a guideline. It says take care of the place you already have. Earth is not just your current address. It is a rare, fragile island in a sea where most of the real estate is empty, frozen, or blazing hot. Even if habitable planets are common, they are separated by light years. We do not have a spare Earth parked next door. If we break this one, the universe will not send a replacement. Seen in that light, climate change, ecosystem collapse, and nuclear weapons stop being local policy issues and become cosmic ones. In a galaxy where intelligent life might be rare and communication is throttled by light speed, every world that wakes up matters. If we are alone for dozens or hundreds of light years in any direction, then our survival is not just about us. It might be about whether this particular patch of the universe gets to know itself at all. There is a moral angle hiding here. If we are one of the few or the only technological civilizations in our neighborhood, then kindness and knowledge take on extra weight. Every act of compassion, every scientific discovery, every piece of music or story or art we create becomes part of the only record of consciousness in this region of space. The universe is not judging us, but we can choose to treat our brief moment of awareness as something worth using well. Light years also give us a strange kind of comfort. When your problems feel huge, when anxiety about the future swells until it is hard to breathe, stepping back to the scale of the cosmos can help. Not because your pain does not matter, but because it is framed. The same brain that worries about bills or relationships or career paths is capable of understanding galaxies and cosmic horizons. That contrast can remind you that your life is both very small and incredibly rich. Look at it this way. You are made of atoms forged in stars. The iron in your blood, the calcium in your bones, the oxygen you breathe, all created in stellar cores or in explosions that ripped stars apart long before Earth formed. Those atoms drifted through space, became part of a new star system, cooled into a rocky planet, joined oceans and rocks and air, and eventually assembled into you. Now, for a few decades, they get to look back at the stars and understand that whole journey. The light year wraps all of that into one idea. It says the universe is vast beyond your intuition, that distance and time are deeply intertwined, and that there are hard limits on how fast anything can move or communicate. It also says that within those limits, something remarkable has happened here. A species has appeared that can map those distances, measure those times, build machines that reach into space, and create meaning out of it all. Next time you stand under a clear sky, remember what you are actually seeing. Some of the light hitting your eyes left its star when you were a child. Some left before your grandparents were born. Some began its journey before humans built cities or discovered agriculture. A fraction comes from galaxies so far away that the light has been travelling for billions of years. You are not just looking up. You are catching messages that have been in flight longer than any human story. You are small in that picture, but not irrelevant. You are one of the ways the universe has learned to feel awe about itself. You can hold in your mind both your own fragile life and the knowledge that stars are separated by light years, galaxies by millions of light years, and the observable universe by tens of billions of light years. You can feel humbled and empowered at the same time. That is what light years really give us. Not just a tool for astronomers, not just a definition tied to the speed of light, but a new perspective on what it means to exist at all. A reminder that we live in a vast, indifferent cosmos, and that within that cosmos, for a brief moment on one small world, something has appeared that can understand and care. That something is us. And for now, this is our corner of space to explore, to protect, and to fill with meaning.